Hello students and welcome. In this last section in chapter 3 we're going to discuss additional topics in probability and counting. The first topic in this section is about permutations, and the definition and formula are given on page 168. So a permutation is an ordered arrangement of distinct objects. So by distinct we mean that all the objects of interest to us are different from the others. So for example, you could think of these three objects which are different colors. Okay, so none of the objects repeat themselves. So that's why they're different. So the formula for the number of ways to arrange n different objects is given by n factorial. So the exclamation point means factorial. So in math, whenever you see an exclamation point, it does not mean that you exclaim or yell the expression out loud, right? It just means it's factorial. So the exclamation point means factorial. So let's say, for example, we want to figure out the number of ways we can arrange these three objects, so the red circle, blue circle, and green circle. So one way to approach it is to come up with all the possibilities that we can arrange these three different objects in order. So, for example, one possible arrangement of these three objects is red, blue, green. Okay, another possibility with red coming first is red, green, blue. All right, and there's no other combination with red listed first. So let's try another color first. So let's say blue comes first. Right, then we can follow that with red and green. And likewise with blue first. Another possibility is blue, green, and red. Right, and you'll quickly see that there are only 6 possibilities. Okay, so in other words, there are 6 different permutations of 3 distinct objects. Okay, and then these are the possibilities for listing these 3 objects in different orders. So even though we're looking at the same 3 objects, right? These are all different permutations of these same 3 objects. Okay, and these are different permutations because each arrangement, such as green, blue, red, or green, red, blue, is in a different order from the others. Okay, so according to the formula given in the book, okay, the number of different arrangements of n distinct objects is n factorial. Okay, so on our calculators, we can go to 3, so number 3, type in the number of objects you have, and then find the factorial function. So depending on your calculator, right, the factorial function may be directly above one of the buttons. Okay, so for example, with the factorial notation, the exclamation point is above one of the buttons, right? You might want to press the second button followed by whatever button the factorial function appears above. But on this calculator, the factorial function is in the probability menu, PRB. So go to the PRB menu if necessary, and then scroll down to find the exclamation point, which means factorial, press enter, and then enter again. And it tells you that 3 factorial is equal to 6. You can also look at the example that they have in the book. So example 1, find the number of permutations of n objects. Okay, and it has a picture of a Sudoku puzzle. All right, and the question is asking how many different ways can the first row of a blank 9 by 9 Sudoku grid be filled in? Okay, so since the numbers 1 through 9 must appear in the cells in the top row, right? The number of ways that you can write the numbers 1 through 9 in the top row is 9 factorial, which is this number here, so 362,880. So the next topic also involves permutations, but it's specified by saying that we're taking a permutation of n objects r at a time. So in other words, if we have n distinct objects and we wish to arrange a subset of them, right, then the formula is given by this equation. So NPR, right, where the P stands for permutation, so it's equal to n factorial divided by n minus r in parentheses factorial. Okay, so if we have a bunch of different objects and we want to figure out the number of ordered arrangements of a subset of those objects, right, then we use this formula, right? But if you want to arrange all of the objects, okay, then we use the other formula, n factorial. Okay, so in this formula here, r is the number of objects from the n we wish to arrange, and we specify that r must be less than or equal to n. So if we wish to arrange a subset of n items, okay, and the number of items we wish to arrange is r equal to r, right, then r must be less than or equal to n. So let's take a look at an example of where we might use this formula. So we have example 2 on page 169 on the topic of finding finding a permutation of r objects from n, NPR. So the problem says find the number of ways of forming 4-digit codes in which no digit is repeated. Okay, so I've rewritten the problem here. So example 2 on page 169 says to find the number of ways to make 4-digit codes where repetition of digits is not allowed. Okay, this could be useful when deciding on a PIN number for your credit or debit card. In any case, when it says a digit, right, what is a digit? So a digit is a single number 0 through 9. Okay, and if you count them, right, you'll see that there are 10 digits 0 through 9. So if we're not allowed to repeat digits in making a 4-digit code, like for example, let's say I'm trying to decide on a PIN number for my debit card. Okay, and let's say I want the first number to be a 9. Okay, so once I use that 9, I can't use it again. Okay, so I can cross that 9 off my list. Okay, let's just say, let me pick another number like 2. Okay, once I use the number 2, right, cross it off, can't use it, so I got to use the other remaining digits. Okay, likewise, let's say I want the next number to be 4. Okay, cross that off. Okay, and let's say that I want the last digit to be 7. So in other words, if no repetition of digits is allowed, right, all the digits in my 4-digit code must all be different from each other. Okay, so for example, the code 9247 would be allowed, right, because none of the digits are repeating. Now, if I were to repeat digits, okay, for example, right, I could use the 9 more than once. And let's just say the third digit I want to be an 8, and the last digit I want to be 1, right? So for example, 4-digit codes where a digit is used more than once is allowed. Okay, so with the description given in the problem, right, the pin number or 4-digit code 9247 is allowed. Okay, while the other code is not allowed. Right, since we cannot repeat digits. Okay, so you can look at this problem as being a permutations problem, right, where you have 10 digits to select from, and you only want to select 4 of them, right? That's essentially what this is. Okay, so it may not be obvious that this is a permutations problem. Okay, but basically we can use the permutations function on a calculator to get the answer. Okay, so the number of objects is 10, because we have 10 digits to select from, so n is equal to 10 digits to select from. Right, and we're only selecting r equal to 4 digits to be in the 4-digit code. Okay, so on our calculators, let's go ahead and enter the number 10. And then you want to go ahead and find the the permutations function. So it may look like as NPR, okay, as you saw it in the book, NPR, or as you saw in the formula, NPR. So look for that function in a calculator. So this particular calculator, the permutations function, is in the probability menu. Okay, it's the first one listed here, NPR. Okay, so be sure to enter the value of n first. Okay, followed by that function, press enter. Okay, and followed by the number of objects that you wish to arrange, which is 4. Okay, we can see that there are 5,040 different pin numbers, right? If we do not allow repetition of any of the digits. So 5,040 4-digit codes, okay, are possible, okay, if we do not allow repetitions. Okay, so before we move on to other topics in this section, I want to revisit a topic that we discussed in section 3.1. So it may not be obvious why we use this formula, or why the formula looks the way it does. Okay, so instead of using this formula, right, try using the appropriate function in the calculator, which I just showed you. Okay, the other thing I want you to be aware of is that both permutations formulas above, right, this one here, and then the n factorial one that we talked about earlier, okay, are actually based on the fundamental counting principle that we discussed in section 3.1. Okay, so we can quickly revisit that in the book. So page 132 is where you find the fundamental counting principle. Okay, and it basically says that if an event can occur in m ways and a second event can occur in n ways, right, then the number of ways that the two events can occur in sequence is m times n. So you may remember that we did an example about access codes. Okay, so I encourage you to look at example 4. I'm not going to do it, but I encourage you to look at example 4 on page 133 since it uses the fundamental counting principle. So the question is, can we use that fundamental counting principle to help us solve this problem? Example 2 on page 169. And the answer is yes. So if we think about the total number of 4-digit access codes that are possible, okay, all we have to think about is, okay, is in how many ways can we choose the first digit? Okay, so assuming we cannot repeat digits, right, how many ways can we choose that first digit? Okay, so when selecting your first digit in this code, right, you have 10 digits to start with, so you have 10 possibilities for that first digit. Okay, and then after you select that first digit, you cross it off. Right, so how many more digits can you select from? So remember, we can't repeat digits. Okay, so after selecting the first digit, we have 9 more to choose from. So we have 9 there. Okay, then after selecting the second digit, right, crossing it off, right, how many more digits are left? So we have 8. And then after selecting the third digit, we have 7 more digits. So if we do 10 times 9 times 8 times 7 on your calculator, right, it should give you the exact same answer. So in other words, without having to use the formula, the permutations formula, we can use the fundamental counting principle and get the same answer. So we get that there are 5,040 different four-digit codes possible. So that's another way to look at the problem. All right, and you may remember that we talked about arranging the number of ways we can arrange all 3 of these objects. Well, it's based on the same counting principle that we talked about in section 3.1. Right, so if you want to quickly figure out the number of ways you can arrange these 3 objects, okay, we saw that it was 6. Right, so for example, you choose the first object, whatever it might be, the red, blue, or green one. Okay, so there are 3 ways to choose the first object. Then after you choose the first one, then there are 2 ways to choose the other 2. Okay, followed by 1 way to choose that last one. Right, so we see that 3 times 2 times 1 using the fundamental counting principle will still give us 6 possible ways to arrange those 3 objects.